Welcome to our talk, Perceptually Guided 3D GS Streaming and Rendering for Mixed Reality, to learn how we move 3D GS one step closer to being truly MR ready. The recent wave of 3D GS has unlocked real-time, high-quality rendering across many applications. However, MR, especially untethered MR, imposes far more stringent performance constraints: refresh rates above 60 Hz, retinal resolution stereo rendering, and tightly limited compute and power budgets. Even the most efficient and scalable 3D GS variants still struggle to meet these demands. Meanwhile, MR displays span a wide field of view and directly expose the non-uniform nature of human vision. Because peripheral vision has much lower acuity than foveal vision, this has motivated foveated 3D GS. However, foveation alone does not fully characterize human vision. The luminance, contrast, and spatial frequency of local scene content also strongly affects their visibility. So, how can we do better? Our key idea is to adaptively balance perceived quality across the visual field through continuous level of detail modulation. At the core of our method is a perceptual model that takes the user's current viewpoint and a target quality level and predicts for each direction in the visual field the minimal LOD required to achieve that quality. The result is a spatially varying LOD map that allocates Gaussian budget where it matters most to maintain perceptually consistent quality across the scene. This enables scene-aware, gaze-contingent adaptation while also supporting flexible, budget-driven quality control. Our method proceeds as follows. First, we construct a continuous LOD structure for 3D Gaussians by adapting the tree representation from hierarchical 3D GS. Here, LOD is defined as a screen space projected size threshold. Gaussians corresponding to a particular LOD can be efficiently retrieved via a cut over the tree structure. Second, we adopt FOV video VDP, a visual quality metric that models the spatial, temporal, and eccentricity-dependent characteristics of human vision. We use it to generate data tuples of viewpoint perceptual quality measured in just objectionable differences, or JODs, and corresponding LOD values, and distill this knowledge into a lightweight perceptual model for scene-aware, gaze-contingent LOD prediction. Third, we partition the visual field into a dense grid of viewing frustums and apply the spatially varying LOD map to control Gaussian budget for each frustum. This allows us to render only a perceptually sufficient subset of Gaussians under a given compute budget, while minimizing visible quality degradation. Lastly, to better support untethered MR, we introduced an edge cloud collaborative rendering framework that offloads these compute-intensive steps to the cloud. At runtime, the edge MR device transmits the user's current viewpoint and target quality level to the cloud and receives a binary mask specifying the subset of Gaussians to render. To support our investigation in immersive MR settings, we constructed 4 high-quality image datasets featuring photorealistic scenes. Now let's look at some rendering results using our perceptually guided method. As shown in these visualizations, our method adaptively allocates Gaussian budget through spatial LOD modulation across varying eye gaze positions and also different Gaussian budget levels. We compare our approach against 2 baselines: hierarchical 3D GS with uniform LOD and foveated 3D GS with eccentricity-guided LOD. As illustrated in these zoomed-in insets, our method more effectively allocates Gaussian budget across the visual field and better preserves high contrast and high frequency content in the periphery. Objective evaluation validates that our method consistently outperforms the baselines across varying budget levels. Of course, perceptual improvements ultimately need to be validated by human observers. Therefore, we further conducted an MR user study with 16 participants using a pairwise comparison protocol. Once again, our method achieved the highest user preference among the 3 approaches. In summary, we introduced a perceptually guided LOD modulation approach and an edge cloud collaborative rendering framework for 3D GS. By aligning Gaussian budget allocation with human visual perception, we move 3D.js one step closer to being truly MR ready. Thank you for listening. We hope you find our work inspiring and interesting, and we invite you to try out our released code.